high energy ions. Define high energy ions as 2 MeV approximately, and they're scattered from the atomic nuclei in a sample. The energy of the backscattered ions then can be measured to give information on the sample composition as a function of depth. Start off the morning with a little bit of history. So, the Geiger-Marsden experiment was performed by Hans Geiger and Ernst Marsden in 1909 under the direction of Ernest Rutherford. The prevailing theory at the time was, okay, this is back before we knew for sure what an atom looked like. And so the prevailing theory at the time was that you had electrons in an area of a large positive charge, just well distributed, because they had some information on that. And so this is what they call the plum pudding model. And so to test it, what they would do is they would shoot alpha particles through a thin foil, and they put a detector behind it, and the alpha particles, being very massive, would just go right through. And so everyone's saying, see, this is not a problem. It proves our theory. But he needed something for his graduate student to do, so he said, hey, when you get a chance, put the detector on the other side, on the front side, because nothing should come back. Well, the graduate student did it, and lo and behold, he got counts. And so they said, oh, well, that means that our whole philosophy on this can't be right. And so then he said, well, what if instead of having all the positive charge widely distributed, we put it into a small ball right at the middle, i.e. a nucleus, and then we had electrons going around like planets. And hence that was the planetary model that he came up with. Even this drawing here has the nucleus way too big. The nucleus volume is about 1 × 10⁻⁴ of the total volume of an atom. Here at the MRL, we have one main instrument that we do Rutherford backscattering with. It's our 2 MeV Van de Graaff accelerator. Actually can run from about 0.7 to 2.4 because we can also do ion implantation on it. It has a beam size that can go from about 1 to 3 millimeters. If you're going to use it, you're going to have a flat sample, and your sample can be rotated while it's in there. So this is the Van de Graaff accelerator, so if you're wondering what that is, remember back to the guys at the science fairs where they have the accelerator there, you put your hand on it and your hair stands up. Same thing, except here we're going to much higher voltages, so therefore we actually put it inside a pressure vessel, which is at about 7 atmospheres to keep breakdowns from happening. So, when we do sputtering, like Rick had talked about yesterday, we're generally working in the hundreds to thousands of eV. But now when we're doing RBS, we're up in the MeV region. So now what that means is you can pretty much ignore hard interactions with the electron shell because you have so much energy. And so now instead of thinking of a crystal like this, which shows us lots of electron shells, we actually are just talking about the nucleus. And so you can see here you have no space to go through, but here you have plenty of space to go through. And so that's what happens when you're at the very high energies. And then as you get to lower energies, then of course we have nuclear scattering off the shells again, electron shells again. The electrons do have an effect though in the process. It kind of acts like a little drag. So like if you were throwing a football through the air or a baseball through the air, eventually the baseball slows down as time goes on because you have a drag effect. And the electrons do kind of do that, and we use that to our advantage. But first, we'll talk about the elastic two-body collision. So this goes back to your freshman level physics courses, right? So we have conservation of energy and conservation of momentum. Incident ion comes in with a certain energy, hits target ion, it gets scattered, and then there's a recoil in the target atom, and you can have some angles associated with that. Classic billiard ball collision, both energy and momentum are conserved. The energy of the scattered atom then is related to the masses involved and the detection angles. And so we can define the kinematic factor K like this. And so from the kinematic factor, we can see that when we have a high mass, we have a situation where we have a lot of sensitivity. So we have a lot of backscatter. But at the low mass, we lose that. But we actually end up with a situation where we have high selectivity at low mass. And I'll talk about that a little bit more. With RBS, we're using a mass of 4 for the helium. So that means that we are able to get backscattering. If you're working with lighter things, you're using hydrogen, you could only get some forward scattering. Or, I take that back. You have to use something like hydrogen to be able to get forward scattering. Since the nuclei have a Coulomb interaction, we can actually determine an exact expression for the backscattering, and thus RBS is a quantitative method. We tend to define a cross-section, scattering cross-section, as a function of energy and scattering angle, which is proportional to the atomic number of the film divided by the energy and then the quantity squared. So then, instead of talking about masses when we're working with this, we end up talking with the atomic numbers. And then the second thing that we talk about is electron stopping. So we can think of the electron clouds as having like a little drag effect on the helium as it goes through, the alpha particles as they go through. And so you can kind of think of it, like I said, it's a projectile flying through air, although in reality you're talking about electric fields, not air, at these sizes. And so the drag then is on the primary ions, which can, because of that, it can give us information on depth. So like to say that usually when you look at a spectrum, you get a convolution of the thickness and the material. And so then you can use that information to pull both of those out. So basically, the deeper the backscattering event occurs in the sample, the lower energy it'll have. So for instance, if we have a backscatter event right at the, so we have a platinum silicon mythical alloy. And so we have a backscatter event that occurs right at the surface. If it occurs right at the surface, we're going to have the backscatter event. It's going to lose some energy depending on what it scatters off of. If it's platinum, it drops just a little bit and comes out, and so we have an energy, we don't lose very much energy. But say it backscatters off the silicon, well then it drops down a lot more energy before it comes out. Now if the ion travels through the sample, it's losing energy, losing energy, losing energy, has a backscatter event, drops that same amount, this size and this size are the same, and then it comes back out. And so now it has a lower energy than the backscatter event that occurred at the surface, and from that information then we can determine thickness. And the same thing off the silicon. So we actually get a signal from the whole region there. And this kind of shows that as well. Re-showing the kinematic factor here. And so basically we made up a hypothetical alloy, again, of 20% gold, 20% indium, 20% titanium, 20% aluminum, 20% oxygen on carbon. The idea behind that is we're basically doubling the atomic number, more or less, as we go through. And so from this you can see, looking at the kinematic factor, we have good sensitivity at high mass. So even though we have the same amount of gold as we have oxygen, we have a much bigger peak for a very thin film, 10 monolayers thick. And as we go to lower Z, we are dropping in our sensitivity. But we have much better selectivity at low Z. So the oxygen and the aluminum are much more further spaced apart than, say, the indium and the gold. So that means that if you're trying to determine what you have, it's easier if you have low Z materials. If you're trying to determine how much you have, it's easier to determine that with high Z materials. So now the second thing that this shows is what happens when you get thicker and thicker films. So as you see here, 10 monolayers, you have a very thin film, you have a very sharp peak, and the width of all these peaks is effectively the same. As you go thicker, of course, they get broader, and as you go even thicker, they start to interact. Of course, they're going to start interacting first at the high Z materials because those are closer together. And it's just a sum. It's just a sum. So the counts from one plus the counts from the other. And also you see, for instance, let's look at the titanium here. You now have the front surface information and then the back surface information of the film. So it goes up, has a plateau, comes off, because the concentration isn't changing throughout the thickness. And then you can also see, as we go to thicker and thicker, our maximum counts are going up higher, because we're getting more and more counts. And then finally, you can see as you go thicker and thicker, eventually everything kind of works its way together. And so it does kind of put a maximum thickness onto what you can kind of use effectively with the technique. The one program that we tend to use most for analyzing this, simulating our spectrum, is the SIM-NRA. Another program that was used more before was called RUMP. Both of them have certain advantages. This one tends to be easier to use for people. So of course the analysis of this requires knowledge of the scattering cross-section, but these are known as a function of scattering angle for all elements. And it doesn't matter what they're next to. It's just that individual atom. So then we can simulate and fit the data if we know something about our sample to start with. Usually we kind of know something about the composition, something about the thickness, and so we can work from there. There are important fitting parameters that we have to go. These are, experimental parameters. The incident and exit angle of the beam coming in and out. The energy calibration and offset. The energy calibration offset actually can be figured out from the starting surfaces if you have multiple starting surfaces. So that allows you to calibrate your x-axis so that you can get that information. And then, of course, the layer thickness and concentration allows us to get is stuff you put in, but then you can solve for. And so you can actually do the fitting of your curve that way. And so this shows a fit with 27% hafnium, 1.8% zirconium, 13% aluminum, 50% nitrogen, and the balance of oxygen. And then, of course, to show this again, hafnium is much, much higher Z, and so you have a huge peak for 27%. Zirconium is also quite heavy, and so you can see the 1.8% pretty easily, but you have to have almost 13% aluminum to have the same amount of counts that you get from the zirconium. So, thickness effects. So as I was mentioning a little bit earlier, with thickness, so you have a starting surface. So this is a titanium nitride thin film on MgO, simulation of that at various thicknesses. So the top one is 300 nanometers, 400 nanometers, 600 nanometers. And so things that you look at. So when I'm fitting this, I'm looking at the starting surface of the titanium and the nitrogen, where those pick up. And so then this area under this curve gives us information, the width of the curve gives us information on the thickness. And as you can see, it's thin enough such that the substrate, magnesium and oxygen, where they start, comes up before where the nitrogen is from the surface. So again, like I said, we have a convolution of mass and thickness when we're working with these. If you go to 400 nanometers, you actually have a situation where the magnesium is coming up at the same time that the nitrogen from the surface is coming up. So there's some confusion there if you were trying to fit this. And then, of course, if you go to thicker, then, of course, the nitrogen starts before you would see the substrate. The key here is that the leading edges of the titanium and the nitrogen do not move. They're at the same energy. It's that the leading edges of the substrate are moving deeper and deeper as you get thicker films. The key here that you can pull out of this is with RBS, it's very nice to run simulations before you grow your films to make sure that you can see what you're interested in looking for. We can kind of also play off it a little bit with our system. We have two angle setups that we can use. So we have incident angle effects. So one of them is you have the beam coming in and then the beam coming out with 15 degrees in both cases, and that was what we used for the simulation before. But also we can be using other angles where we're coming in where we have a 52 degree, a different scattering angle. At a higher incident scattering angle, the beam will spend more time in the sample, just like we talked about with the angle resolved XPS yesterday. If you come in at a steeper angle, or even the X-ray that Mauro talked about, glancing angle X-ray, you come in at a higher angle, and so therefore you spend more time in the film before you come back out, before you have your scattering event. And so that makes the width of the elemental bigger for the same thickness. So you can kind of consider that to be more surface sensitive. This is an example showing average compositions. This was actually a multi-layer titanium aluminum nitride, titanium niobium nitride. But of course the thicknesses are too small for us to resolve individual layers. But so the key here though is by knowing our constituent elements, we can kind of determine both the thickness of the layer and then the average composition of the alloys. And so we have information for the niobium, the titanium, and the aluminum. And so we were able to get an average type composition. Finally, this was an experiment done looking at the oxidation of a titanium nitride film on silicon oxide. And so this shows the experimental and the simulated spectra done through by Rump. And so as deposited, we have a nice titanium peak. We have a nice pickup from the oxygen, and then the nitrogen is here. After annealing, you can see that the front part of the titanium is decreased, and we have more oxygen signal here at the surface. And so from this, from the titanium, you can actually see how much it's decreased, and it makes sense because you're going from a 1-to-1 correspondence to a 1-to-2 correspondence, so you should have 1/3 less, and then the oxygen coming up. And so you can actually, from this width, you can actually figure out how deep your oxide layer is. So to summarize quickly for the RBS portion, we can get quantitative information for the elemental composition, but it does require flat samples and a pretty significant beam size. And yes, if you have a very soft sample, the beam can do some damage to your sample. But otherwise, it's non-destructive. And the detection limit varies from 10% down to 10⁻⁶, depending on the Z of the material. So it's optimum for figuring out heavy elements, the concentration. It works best if you have heavy elements on a light matrix, so something on carbon, or in my case when I was doing my graduate work, silicon germanium on silicon. And then you can get depth information from monolayers up to about a micron. Next, we're going to move into secondary ion mass spectrometry. So basically, like Rick talked about with the OJ and the XPS, we have something coming in and something coming out. In this case, we're going to use ions in and ions out. So SIMS is an analytical technique based on the measurement of the mass of ions ejected from a solid surface after the surface has been bombarded with a high energy primary ion. And in this case, high energy is not the same high energy that we used for RBS. It's about 1 to 25 keV primary ions. And so yes, we're talking about electron clouds here in the sputtering process. The measurement of mass allows us to examine isotope differences, which is something you can't do with other techniques. And the technique itself is most effective for concentrations below 1%. So doing a quick technique comparison, Rick quickly showed this yesterday, but we have Auger and XPS using different types of probes. And then we have dynamic SIMS and time-of-flight SIMS. The key here that I want to show is that while the quantification is easier with Auger and XPS, it's much more challenging for SIMS. But we can measure much higher. We have much higher sensitivity. So this is a block diagram of the SIMS technique. We have a primary beam of ions that come in and hit the sample, and then after that we call that the secondary ion beam, similar to like secondary electrons in an SEM. So for ion sources we have many different choices. We use a cesium gun or an oxygen gun a lot of times. We also can use nitrogen or gallium. On the time-of-flight SIMS, we actually have a gold source, although for a lot of the new time-of-flight SIMS, they're also using things like bismuth or C60 or these very massive argon clusters. So that's your primary beam that you impinge on the sample. You try to have a nice small spot size. And then your sample, which must be vacuum compatible, although there's some, when I was at the SIMS workshop earlier, there's a lot of people who are working on ambient mass spectrometries. And then right above your sample, you actually have an extraction field that pulls anything that gets sputtered away that's charged with the right charge away. And then that goes through an energy analyzer onto a mass spectrometer, and then you have detectors. There are multiple options on how we do our mass spectrometry and our detectors. We have two of them here in the CMM for the mass spectrometers. For detectors, you can do things with electron multiplier, Faraday cups, resistive anode encoders, channel plates, etc. And then the type of results you can get out a mass spectrum. If you follow a certain peak as a function of depth, you can get a depth profile. Alternatively, you could do an image of the surface, or of course, you can combine all these into an image depth profile. Now in SIMS, we tend to talk about two regimes of working. The first is dynamic, and so that's what a lot of the early instruments were doing. So this is a situation where you're constantly removing material, you're eroding the material, you get information as a function of depth. But the second is the static mode. And the idea there is, okay, if I only affect 1% or less of the surface, then I can say that this is a non-destructive technique, and if I were to come back to the same spot later and do a measurement again, I should get the same result. And working in the static regime gives you an advantage, because in dynamic, you basically can only get elemental information, but if you work in the static regime, you get elemental and molecular, and so a lot of chemists are using that for their work. Again, sensitivity is where the SIMS really pays off. So we can do down to parts per million, parts per billion for some elements. As a matter of fact, in some cases, you have to actually think, do I have enough atoms there to be able to measure the concentration I want to look at? Because it's low enough. Types of measurements that we do can do in dynamic. When we talk about that, we're talking about mainly doing depth profiles and mass spectrums. If we're talking about static, we're talking about doing a surface image or a surface spectrum. And then we have two main instruments here in the facility. We have a Kamika IMS-5F. We use that primarily for doing depth profiling. A lot of semiconductor samples are mainly used there. And then the TRIF-3, which gets used for pretty much everything from biological samples to tribology to semiconductors, etc. So this is a picture of our Kamika 5F. As you can see, we have the primary ion column, we have a cesium source and a dual plasmatron, impinges on the sample, electrostatic analyzer to do the energy filtering, and an electromagnet to do the mass filtering. Because of the way this is designed, you can only get one ion through at a time. I should say, one mass through at a time, but we can change the electrostatic analyzer and electromagnet quickly enough that we can do quickly switch between them. So if you wanted to follow multiple things. And then our detectors, we have an electron multiplier, Faraday cup, and the ability to do imaging as well. The electron multiplier tends to get used the most. It gives us a very large dynamic range from 0 counts per second up to about 10 to the 5th counts per second. If you have too many counts per second, then you can go to the Faraday cup and go much, much higher. The second instrument that we have is the time of flight from physical electronics to TRIF3 time of flight SIMS. Here we have a gallium option, but we've been using gold beam for our primary beam. Gold is very nice because it's 197 AMU, but you can actually also pull out gold 2 or gold 3 clusters to get even more massive. And that helps when you want to look at large molecular fragments. We also have the ability to use cesium or oxygen for material removal during depth profiling. In this case, the time of flight detection works a little bit differently than what we had on the Kamika, where you're bending it through electromagnet. Here you send in a pulsed beam that hits the surface, and then you generate your secondary ions, and then you put a big electric field on there, and so you're basically accelerating them to a certain voltage, certain potential, and so the kilovolts, and that potential can then be translated into kinetic energy, so that's 1/2 mass times velocity squared. So if you put a detector far enough away, then all the light ions arrive first, the heavy ions arrive later. And so when we send in these pulses, we'll have an X and a Y, and if you're doing a depth profile, a Z position. And so for each pulse, you get a whole mass spectrum. So you have X, Y, Z, mass to charge ratio, and intensity. So it's a 5-dimensional data that gets completely stored on the computer, which makes it very nice for doing retrospective analysis. Basically, if you said, your boss comes up to you and says, you forgot to look for such and such element in your sample, you can say, oh, well, wait, let me just recheck it. Oh, look, we do have it. And then you can show it to them. And you can make a picture out of it or a depth profile out of it. So one of the first things that happens in SIMS is you have ion beam sputtering. So you have a primary ion beam coming in. That's our nice little blue dots here. And coming and hitting your sample. Well, our sample consists of the red circles with some dopant, which is the magenta things. And so we're coming in, we're making a lot of damage here, and things are getting ejected out. Some of them are charged, plus or minus charges. Some of them are just elements by themselves. Some of them are molecules, as you can see, where you have the circle and this dot. You have electrons coming out, you have light coming out, potentially, but we don't really look for light. And you also have primary beam getting sputtered back out. So you have lots of things coming out. The key here to note is that the only ones that we can measure are the ions. So the atoms or molecules that come out that have a charge. So, okay, so how many of what can we measure? So in SIMS, the yield of the secondary ions can be strongly influenced by a lot of stuff, the electronic state of the material being analyzed being one of them. And so we can define an equation like Rick did with the OJ and the XPS, where the secondary ion current of species M, i.e. what we want to look at, maybe our dopant, is proportional to the primary particle flux times the sputtering yield, i.e. how many particles come out for each particle coming in, times the ionization probability, times what is the concentration on the surface, and then, of course, the transmission of the analysis system. Unfortunately, for SIMS, this value for alpha, while we have some information for sputter yield, we know almost nothing for alpha. So it becomes very hard to be quantitative. So like I was saying, so sputter yield generally is between 5 to 15. That's how many atoms come out relative to how many ions you're sending in. And then the iron sputter yield is the ratio of ionized atoms that come out versus the total number of atoms that come out. And so that can vary huge by multiple orders of magnitude here. And it can be influenced by lots of things. Matrix effects. What's it sitting next to? Surface coverage of reactive elements. Did you put something on the surface that helps enhance that signal? Background pressure of the environment. Did you put in a gas that helps enhance the ionization? Crystal orientation of crystallographic axes. That's a smaller effect, but can have an effect. And then the angle of emission. Generally, we always go straight out. But basically what this says is that from first principles, we can't be quantitative with SIMS. We kind of have to do something else, and that something else is usually using a standard. But, you know, I said all these things as a kind of a negative, but we can also use things as say we can use things to be positive. Because one of the big advantages of SIMS is we have tremendous sensitivity. Like I said, we can measure parts per million, parts per billion. So if we've got these things that affect how many of the particles coming out are ions, maybe we can use that to our advantage so we can measure even lower concentrations, and that's what we do. So basically, if you look at the periodic table, up here you have things that are very electronegative, and conversely down here you have things that are electropositive. So with so positive secondary. So if you want to look at, say, zirconium, you would want to look for a positive ion. If you want to look for phosphorus, you want to look for something that's a negative ion. And that. So now, if we use a certain condition, a certain primary beam, we can actually enhance our number of counts. And so with oxygen, basically we can enhance all these things that are in yellow, because you can think of the oxygen, metal oxygen coming off, the oxygen goes by itself, and now keeps an extra electron, the metal comes out with a positive charge. Or you can think of cesium donating extra electrons because it's that loosely bound electron. And so that enhances the signal from these. And then this is basically another way of showing that. This is the relative secondary ion yield for cesium with negative secondary ions and oxygen with positive secondary ions. And like I said before, in general, cesium works best with electronegative elements and oxygen works best with electropositive elements. Highlight here sulfur works very well with cesium with negative ions, but calcium does not. But on the reverse then, calcium works very well with positive ions, but sulfur does not. So generally you have to make these choices. Sometimes when I'm asked to do depth profiles, I'll actually have to do two, once with the cesium and once with the oxygen, so that we can pick up all our elements. But unfortunately, there are some things that just don't work well with either case. For instance, zinc here tends not to work well. Cadmium's another option that tend not to work well with either of these. But we can get around that. If we actually use cesium with positive secondary ions and look for cesium plus the metal, then we actually have a situation where the zinc goes from a low ion yield up to a high ion yield, and the same thing with cadmium. So it's like basically the trick way to get that. And there was actually a couple talks at the latest SIMS workshop that were discussing the use of that in more cases, cesium plus the metal ion. So he said it's very hard to do quantitative work, but it's not impossible. And so generally what we do when we want to be quantitative with SIMS is we use a standard. And one of the best standards that we can use is an ion implant, although I've also used as standards films with a known concentration. And so what we do is we define a relative sensitivity factor. And so that's defined from the level profile as the concentration of the impurity, or the dopant, if you want to say, times the number of counts we get from the matrix, divided by the number of counts of the impurity. So if you want to solve for that, it's very easy to get the concentration. If you want to do it from an ion implant, you basically have to integrate the area under the curve. Not too hard to do. The software can do it for you. And that will get you your RSF value. And then you go to your unknown and you apply the RSF value, if you're using the same conditions, to your sample. The key here to point out is we're always talking about a ratio of the impurity and the counts, a ratio of the counts between the impurity or the dopant atom and the matrix. So if you just showed me counts from your dopant and from two films and said, see, it's bigger here. I'm like, well, what's it ratioed to? By doing the ratio, it also gets rid of some instrument effects. So this is an example of a phosphorus implant in silicon. And this, so let's first just look at the cesium beam work, because that's the most effective. And so we actually have a counts for the silicon and counts for the phosphorus. And if we integrate the area under the curve, we can then change the counts per second into a concentration. And so it turns out very nicely. Phosphorus is one of the nice things, though, being in group 5, you can actually measure it. It will actually make a ion of the other type, positive ion, and so you can actually measure it, but as you can see, the counts per second are like 2 orders of magnitude less. So that says that, okay, we're not going to be as sensitive in this mode. But, you know, if you do the processing, you can make it fit, but what's the effect? Well, you have a much, much noisier signal, but it is doable. I would say also that our depth calibration here is generally done using a profilometer, so it's done after the fact. A lot of times people say, what's your sputtering rate going to be? And I'm like, I can't really know because my beam conditions can change and what I'm sputtering can change a lot. So the most effective thing is make your crater and measure it after the fact. So that can be a problem if you only want to go in a little bit. Sometimes you have to do an extra experiment where you sputter for a long time so you can get your sputtering rate. One more definition, just to talk about SIMS that we hear a lot of times, is mass resolution. We define it as M over delta M, and the reason for that is on a system with magnetic sector, that's constant throughout the whole mass range. Why do we care? Because sometimes we have two masses that are very similar. So for an O2 molecule, 16 mass times 2 is 32. Sulfur mass 32. So you would think that they would be right on top of each other, but the fact is with the elemental, you're going to have just the fact that you have all these things holding the nucleus together, you actually lose a little bit of mass, give it to energy. And so the mass of that is slightly less than that of oxygen. And so if you have high enough mass resolution, in this case you need about 1600, you can resolve these two peaks from each other. Now the magenta line is what it would look like on a linear scale, but a lot of times when we're working with SIMS, we'll often look at things on a log scale because we're talking about, you know, orders of magnitude changes. And so that's the example that we're showing with the blue. So the log scale helps enhance your lower signal so that you can see what you have. The downside to that is sometimes if you're looking at a mass spectrum, you see peaks at every AMU, and then it's not as nice. This is an example on our Kamika that we did with a depth profile application. So this was a gallium arsenide thin film that was doped variously with silicon or carbon, and they were seeing some passivation of acceptors in the film, and so they realized that it was hydrogen. And so what they did was they did a depth profile and then followed silicon, carbon, and hydrogen, and you can see that the hydrogen goes up where the carbon doping level is, and so, but not necessarily where the silicon doping level is. And then if they anneal it, the hydrogen actually leaves the sample surface, and they were getting better results from that. What does this show us? Well, one of the things that I always point out is 1, 2, 3, 4, 5, 6 orders of magnitude in the dynamic range. So huge changes in concentration that we're able to examine here. And the second is, hey, we're seeing hydrogen. I don't know of too many techniques out there that can see hydrogen. And so we have the ability to do that with the SIMS. Another element that's often hard to see is lithium, and we see that just fine. This is an example of some isotopic analysis that was done for nickel-3 aluminum that was annealed. and 18 oxygen and 16 oxygen. So this allows you to, by using the two different isotopes of oxygen, you can see which part is actually annealing and what the mobile species is. These results actually, Rick Hosh here was actually one of the people on the paper who they were able to show that both the nickel and the oxygen diffused during the process. And so this is an example of combining some Auger work with the SIMS work, because the Auger can't tell you the isotopes, but since we're measuring mass in SIMS, you can actually get information on the isotope and the way those are moving. And then this was actually some work that I was involved with. We were looking at some highly boron-doped films of silicon grown on silicon in a gas source MBE system. And so you can see here that we have boron doping levels that we can measure from 10 to the 16th all the way up to 3 times 10 to the 20th. And so these were grown in a gas source MBE system with constant silicon flux, disilane flux, and a varied diborane flux. Something that's interesting, you can see here the leading edge kind of falls off. It doesn't come straight down like it did here. And that's because of surface segregation. So the boron likes to stay on the surface as you're growing. And so when you turn off the boron, you still have some that's coming out into the pure silicon layer. This is another example of some boron-doped silicon showing that you can do very, what they call delta-doped layers. And as you can see here, the thicknesses are very thin for the for where it drops off, you know, because these are orders of magnitude changes. So it gives some information on the depth resolution of the technique, which is, you know, can be nanometers if you want a depth profile slow enough. The depth resolution in the SIMS can have an ion mixing effect. So you can do some things to help with that. So as you can see here, the blue curve, this is just using 17 keV and looking at carbon atoms, 17 keV primary beam energy. And so you have some mixing. So the tailing end of the delta dope extends out further. But if you do some things like looking at the cesium plus carbon and have a different incident angle, then you can get a sharper peak. And so you have less effective mixing. But what this tells me is if you want to see how sharp your interface is, always look for a leading edge, not necessarily a trailing edge. So just kind of what we've been talking about mostly right now is dynamic SIMS, where you have a primary beam coming in, you're removing a lot of material, you're looking at elementals, you're doing depth profiles. With our TRIF3, we can actually do also static SIMS. And so this gives us ultra-surface analysis of elemental or molecular species. And the key here is that we have the analysis complete before a significant fraction of the molecules are destroyed. One of the neat things about this theory is, and Professor Garrison from Penn State has done a lot of simulations with this, when you have the ion impact, things that come off near where the ion impact tend to be atomic. But as you go further away from there, you can get larger and larger molecules coming off. One thing I talked about with the time-of-flight SIMS is that you're not bending it through electromagnet, you're just waiting time for the ions to reach the detector. So you can actually have huge mass ranges. Now, we don't generally see up to 10,000 AMU. But more like 1,000 AMU in most of the samples with our system. But this was just an interesting situation where we had a gold slide coated with gold that we were imaging, and the gold clusters come out very nicely up to, I think that was 50 atoms in size, this type of cluster up at 10,000. So with the time-of-flight SIMS, you are not limited to working at low mass resolution. You can actually get good mass resolution. So example here, about 11,000. This peak showing all three of these occur at the same nominal mass of 39, but you can resolve each of them for the organics. Just a little rule of thumb for SIMS, organics tend to appear at slightly higher mass slightly higher than the number, so slightly higher than the 39, the integer number, whereas elementals, if they're heavier than carbon, show up slightly below. And that's one quick way you can say, this is probably an elemental, or this is probably a molecular species. One thing about the TOF SIMS, when we're talking about mass resolution, you really have to say what mass you're looking at, because I said m over delta m is defined for slit-based systems, whereas the time of flight is not a slit-based system, so it actually varies across the mass range. So you may have something like 400 at hydrogen, but you're at 10,000 for gold. So you generally, when people are writing papers up, they'll say my mass resolution was blah at 4 mass 28 or something like that. We can also get pretty good lateral resolution in the time of flight SIMS. These are some quantum dots, indium arsenide on gallium arsenide quantum dots. Each of these dots from the line scans you can see here have about a half micron in width. This was done with an indium source. We're using the gold source, so our resolution is not quite that good. But we can also get really good depth resolution with either system. So this is a aluminum gallium arsenide multilayer. And so you can see the aluminum going, when the aluminum goes up, the gallium goes down, and vice versa. They actually did this measurement with multiple instruments, this sample, and it traces the same way on both of them. So the fact that we have much stronger gallium at this point and much weaker aluminum is actually true for this sample. And so this shows that we have approximately one period in this every 2 nanometers in depth. This is a local experiment that was done by Josh Ritchie, who graduated from, I think he's graduated now, from Ralph Nuzzo's group, where they grew deposited a molecule down on substrate, and this molecule can actually break the influence of a certain wavelength of light, and so it breaks here, and so basically he's like, okay, so we can put a mask on this and we can have some of it shown with the light and others not. Can we see the difference? And the first molecule that they brought to me, it was just all carbon and hydrogen. There was no difference. So then they brought something that was just covered with fluorine, worked perfectly. And so he goes, but that doesn't help me. That's not a useful molecule. And so he said, what if I put a bromine on this? And so that's what he did, and we were able to get some good results. It's kind of interesting in this experiment, though, because you don't immediately see it. You have to collect for a little while before you can get it. And so here's an example. So the brighter color is the bromine signal that we're seeing on this. And so this is where the whole molecule is intact, and then where the bromine shows less, the molecule isn't intact. And we actually see a change in the sulfur. The sulfur is true for both cases, but because of the shielding of the larger molecule, where we have the bromine, we don't see it as well. So where we don't have the bromine, then we see it better. And then this is an example I scanned in a little bit closer to kind of show some high resolution work right here on the little X. And so this is a 50 micron scan. With our current software, all of our scans make 256 by 256 pixel images. And so that means that we've got about 5 pixels per micron on that. The other thing to note is the bromine, even from this, was not visible in the XPS. So you needed the higher sensitivity of the SIMS to make it work. This is some biological work that was done early on by Eric Monroe in the Sweedler group. And so they were looking at the vitamin E distribution in the cells, in some cells. And so what we see here is a mass spectrum and then some images that were created from different masses. So vitamin E occurs at mass 430. And so this, but we have all these other peaks, so we don't know what necessarily they are. And so that's part of the difficulty with doing SIMS, TOF SIMS, is that you get lots of peaks, but you don't know what they are. And so generally what you need to work from is a lot of standards where you do know what they are and see what kind of mass spectrum they produce, and then you can start applying those to your unknowns. And so they knew where vitamin E was, they knew where phosphatidylcholine was, they knew where choline was. And from the fact, this strong peak here, they didn't know what it was, but from the fact that it was localized at the same spot where they were seeing the vitamin E, that allowed them to say, oh, this peak comes from vitamin E then. It's just a fragment of the vitamin E. And then this is an SEM image. The interesting thing that Eric was able to find out is if you starve a cell, they know vitamin E is very important in how the cells work, but if you starve a cell from vitamin E, it actually locates right here where what they call the process comes off the cell, where it goes out and talks to other cells. So they figure that vitamin E is actually very important for communication between cells. And so that's why that's the last spot that it leaves in the cell. Kenzie Amaya, working from the Clayton group, actually was doing work on songbird brains, tissue slices from them, and they wanted to see what's the difference between, if you put a baby male bird, in this case a zebra finch, in with other birds, it will learn to sing. If you do not put it with other birds, it will never learn to sing. And so they wanted to know what kind of changes occur in the brain. And they showed that there's a localization of certain fatty acids in the RA and HBC sections of the brain. I'm not a brain scientist, so I don't quite know where all those are. But this localization increases after post-patch day 40. So, what was funny about this was he needed a very big area scan, and so what he ended up doing was taking individual 600 by 600 micron scans and slightly overlapping them and doing a whole map across the surface. And then he went over to Beckman and the Imaging and Visualization Center and was able to stitch them together. So of course, this happened early in his degree work, and physical electronics, said, oh, well, our large areas aren't working, so we're just going to rewrite the software and make it so our software does this automatically. And so some of his later work where he's graduating, he didn't have to do all this hard work. But this is, if I remember correctly, 194 individual 600 by 600 micron scans here. We also have done some tribology in our SIMS. This is an example of some diamond-like carbon films for friction reducing. And so they would have a ball running on a disc in a circle. And so we were able to get the ball and the disc into the SIMS. One thing to note, they started with very flat surfaces, so that's important to note. I've had people bring in rough surfaces and then you can't see the wear tracks. But what they're able to see is the oxygen gets on the edges, whereas the carbon stays in the middle. And so this is an example of something we can do on the top SIMS where we color the oxygen in red, the carbon in green, and then you can do an overlay and show where the various positions are. And then of course, if we have all this information, we can actually make it 3D imaging. And so this is an example showing the wear track with oxygen on the outside. And you can, in the software, you can rotate this around in lots of different cases. And if you want to do it even more fun, you can take each of the individual images at different depths and actually make a movie out of them. So I usually like to show the CQH to it and see how it's becoming more strong as a function of depth. So to give a summary here then for the SIMS, we have some 1 to 20 kDB primary ions that come in, and then we measure secondary ions coming out. We get information on surface mass spectrum, 2D surface ion images, we can do elemental depth profiling or 3D image depth profiling. We have the ability to measure hydrogen and everything above, and we have incredible sensitivity, parts per billion, up to about 1 atomic percent. You can measure higher than 1 atomic percent, but at that point you have to be very careful with matrices. And then finally, analysis, we do about 1 micron up to about several millimeters. Doing a depth profile is a little bit smaller for the take rate. So, and then finally, just acknowledge our sponsors. Generally, there's a lot of fragmentation that's involved under certain circumstances to get that. That's actually one of the big things that we've worked on the last couple of years in the SIMS community is how do we get the whole molecule? And it's not easy. If you use a larger source, that's where C60 comes in and is useful. A more massive source, you have a better chance of having the whole molecule come up as opposed to fragments. You'll always get fragments, but if you can at least get the whole molecule plus the fragments, and so that's why they've been working on these larger and larger molecules. Another thing that is important in the SIMS community has been how do we keep the molecular information as we do the profile? And so that's where the C60 and these really massive cluster ions have been going, because you can actually have a situation where the amount of material you remove is deeper than the damage layer, at which point then you can keep collecting molecular information for deeper.
The things you can do anti and what placebo compared to the
That's the goal, yes, and that's why they're talking about the larger, more massive primary.
You said the RBS, you need a flat sample. How flat? What's the effect of roughness?
Yeah, so of course the effect of roughness is going to, your leading surface, of course, will not be sharp, and that causes problems. So the rule of thumb there, I think, is, microns, tens of microns is probably okay. But it really is going to come down to some simulation, and the way you would simulate that is you would simulate different densities going in. So you have air plus 10%, and air plus 20%, air plus 30%, air plus 40%, different densities. And so that's what makes the simulation much more difficult to do. So it's not a limitation from the technique can't do it, it's just that it's much harder to simulate.
So you're describing RBS as a non-destructive detection, correct?
It can be.
Aren't you getting a lot of dislocations, healing, formation?
Yes. It really then just becomes a question of how much of that is a problem. I know when I was doing some of my graduate work, we do RBS routinely on the films before we would do, and then we take that same sample and make TM specimens out of it. So generally